Hello, if you've just joined us, this is the give back video for the Remove Forces of Motion exam 2015. I'm Mr. Norman. We were just in the middle of this question, which is question 4. And on the previous video, we've already looked at 4A and decided that the force which is causing the athlete to accelerate upwards is the reaction force of the ground pushing upwards on the athlete. And we've decided that what happens, what's shown on this velocity time graph, is that the athlete is going upwards, slowing down, and then falling back towards the ground and hitting it just like that. What height do they reach? We've decided that that must be where they're actually at zero velocity before they come down, because it's when they're at the top of their motion. So if we read that off the graph, it happens at 0.4 seconds, but if we want to know the height from a velocity time graph, we need to work out the area enclosed by that triangle there. So doing that, the area is a half times base times height, which is a half times the base is 0.4, and the height is 4 seconds. So 4 times 0.4 is 1.6. Divide that by 2, giving you 0.8 meters. The 4 marks there for equation, sum, answer, and unit. The acceleration of the athletes during this time. So the acceleration is given on this graph by the gradient. So you can either work out the gradient if you know how to do that from maths, or even simpler using our equation. Acceleration is change in velocity over time. The change in velocity here, well, at the end they're moving at 0 meters per second, and at the beginning they were moving at 4 meters per second. And that change happens in a time of 0.4 seconds. So 0 take away 4 gives you minus 4 meters per second. That's divided by 0.4 seconds, giving us 4 divided by 0.4 is 10, but of course it's minus 10 meters per second squared. The next question asks us what's the direction of the acceleration and how you can tell that from the graph. So just thinking about the athlete, they start off moving upwards and then they stop and they come back downwards and accelerate downwards. So the acceleration is always downwards. So 1 mark for saying that. And how we can tell that from the graph? Well, first of all, you know that from everyday experience that when you go up, you come back down. So the force is downwards, the acceleration is downwards. But from the graph, we've decided already that upwards is positive on the graph because it starts off with a positive upward velocity of 4 meters per second. So because the graph is negative gradient, because the gradient is negative, that tells us that the acceleration is downwards. Positive is up on the graph, so this tells us that acceleration is down. The mass of the athlete is 65 kilograms. What's the force required to cause that acceleration? Force is mass times acceleration. That's 65 kilograms times minus 10 meters per second squared. So the force is minus 650 newtons. Again, the minus tells us it's in the downwards direction. So 1 mark for equation, 1 mark for sum, 1 mark for answer, 1 mark for units. And I didn't worry about the minus sign when I was marking this. What is the force that causes the athlete acceleration? So what's the name given to that force? It's the weight force on the athlete, which of course is caused by gravity. So either of those answers, gravity or weight, would do for the mark. On the next question, we've got 5 multiple choice questions. So just having a look at these, we first are asked about dropping a hammer on the moon, where the acceleration due to gravity is less than that on the Earth. It's only 1.7 meters per second. So if it takes 1 second for the hammer to hit the surface of the moon, what's its average speed during that second? So it starts off not moving at the top, 0 meters per second. 1 second later, if the acceleration is 1.7 meters per second squared, then after 1 second, when it hits the ground, it's going to be going at 1.7 meters per second because it's sped up by that in 1 second. So the average speed is half of that, so 1.7 meters per second over 2. That's the average speed. And of course, that is not going to be any of these answers because they're too big. It must therefore be this answer, 0.85, which is a half of 1.7. For question 6, a Martian picks up a hammer on the Earth and then goes to the moon. Which one's going to be different? Well, the mass doesn't change wherever you are, so it can't be that. The density of the object, well, that's mass divided by volume, neither of which are going to change, so it's not that. The volume isn't going to change, and the length of it isn't going to change either. So the only one that is left is the weight, because, of course, gravity is less on Mars, and therefore it's the weight force, which is the force on it due to gravity, will be less. For question 7, a jet aircraft goes through 100 tons of fuel in 10 hours, and 1 ton is 1,000 kilograms. What's the rate of burning fuel? So if we've got 100 tons, that's the same as, so 1,000 kilograms in a ton, and that happens in 10 hours. So it looks like we're probably, I mean, even based on the units here, newtons per kilogram doesn't make sense. Tons per hour would be okay. Joules per meter is no good. Newtons per kilogram is no good, so it can only be A or D. So we want to know what the answer is from this. So in terms of tons per hour, we've got 100 tons in 10 hours. So that's actually 10 tons per hour. So it looks like D's wrong as well. So A seems to be the only option left. Anyway, let's follow it through. So 10 hours, each hour is 60 minutes. Each minute is 60 seconds. So this is the calculation we're going to need to do. I can cancel a few of the zeros, factors of 10 here. So I've got 10 times 10, so 100. 10 times, yeah, that's right. 100 divided by 1 times 6 times 6. So it's 100 divided by 36. And that looks to be about 2.8, and that's going to be in kilograms per second now. So 100 divided by 36 kilograms per second, so that's about 2.8. So A here is the right answer. Going on to question 8, if we've got a mass of 100 kilograms attached to the end of a spring, it's pulled down a little and released so it oscillates. So we've got this sort of situation, 100 grams, and it's going to go up and down because it's going to sort of vibrate up and down. If in the next 5 seconds it goes through the rest position 10 times, what's the period of oscillation? So if you imagine its position, so its distance upwards, if you like, over time, it's going to, first of all, start off down here, and then it's released. So it goes 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 times through the rest position here. And this happens in the next sort of 5 seconds. So what's its period of oscillation? Here's 1 period, 2 periods, 3 periods, 4 periods, 5 periods. So we've got 5 periods in 5 seconds. So that means that its period, 1 period is going to be about 1 second. C's the right answer there. Finally, for question 9, this question's about units. So if we've got force in gerbils, so that means that gerbils is a bit like the Newton for us, and length is measured in tails. So that means that's a bit like the meter for us. It tells us that, in fact, 1 gerbil is 0.4 newtons and 1 tail is 5 centimeters. Atmospheric pressure for us is 100,000 newtons per meter squared, or 10 newtons per centimeter squared. So these two are the same. What would the gerbils say? So we need to convert the units here. So let's do it in 10 newtons per centimeter. We're told that there's 1 gerbil divided by 0.4 newtons. That's going to get rid of newtons for me. And now I'm going to end up with it in gerbils per centimeter squared. But now I need to get rid of my centimeters squared. So I'm going to divide it by 1 tail squared per 5 squared centimeters squared. So overall then I'm going to have it now in